last Thursday, we did this simple problem. It was a transmission line connected to a load, to a source with an internal source impedance, Z sub S, that was 50 ohms, and then connected to a load. But the load had already a real component, 50 ohms. That real component of the load corresponds to a resistor, right? It had a reactive component that was minus J, 100 ohms. And because it's minus J, it implies it was a series capacitor, all right? Now, to look at this solution, because practically what I asked is to what we did was to, because it's already 50 ohms in the real part, what we wanted to do is just cancel the imaginary part. So that was the just, if you like, of the previous homework, example. And then I think you should follow it from there. We did not have to use the Smith chart. That's what I want to say. Today, I'm going to have a similar example, but where you're going to have to use the Smith chart. And by the way, I will make Smith charts available electronically. But if you want, I'll also in class have on paper Smith charts. And what else? For those of you who will not be in class to take it, you may want to just download it, one of university printers, and if you want to have it on paper, if you don't have the means to draw on the Smith chart and you want to have it on paper, you can bring with you any Smith chart, print it. You can print any of the Smith charts I have on Canvas. All Smith charts are very similar, all right? So I don't want a particular one, but I will bring some in class because in class we don't have a printer. And so that's what I would like to do. So the example we are going to have today.
Excuse me, Professor?
Yes, go ahead.
Are we allowed to use our tablets or iPads during the exam?
Yes, use everything. I said it's open to everything. Use any means available to you, right? I'm not very specific. I don't want you to use particular paper. I don't want you to use particular devices. Use whatever you have available. Use whatever is going to make your solving the problem more comfortable, all right?
So it's going to be available on Canvas and we turn in like our work on Canvas, right?
Yes, yes.
Okay, thank you.
And if you have any questions, I'll be in class, obviously. If for those of you who take it not take it from the class, if you have any questions, please let me know. I'll give you my cell phone. So, or you can email me or you can call me, all right? Or you can text me, but I will not give it broadly to everybody in class. Just email me and I will give you my cell phone. And you can text me if you have any questions, I can respond to you, or I can call you back, for example, all right? So, okay, so now the problem we're gonna solve, and I'm solving the problems here in real time because I think it's easier to follow. It slows me down and it's easier to follow for you what I'm doing, and you can ask me questions while you process the steps that I'm taking. So very similar to the other problem, this time we are going to also have one transmission line with one load. All right, so one transmission line here. And then we always indicate it like that. And at the end of the transmission line, we have a load. But this load this time around ZL, well, I can give you this load in a different way. Let's do it that. A little, not as ZL, I can give you the load as a resistor but now this resistor is in parallel with a capacitor. All right. So at the end of it, you will always have to find the load as a real and imaginary part. All right. Always, before you do anything with Smith chart or so forth. Always you will have to find the load, but this is how I'm giving it to you. And then on the front end is connected to a source with an internal impedance Z sub S, and the source is here V sub S. And now here, let me see, I will do this. I will put here A prime, and then I'll put here B prime, all right? This is where the load is. All right, and now I'm giving you the specifics. This has Z naught, all right? And I'm telling you that, first of all, V sub S is 1 volt. Then Z sub S equals Z sub naught equals 50 ohms. Then I have the length of this line, L, and I give that L equals 3 lambda over 2, when lambda is, in this particular case, I can give you lambda to be 3 centimeters, all right? If I don't give you lambda, I will give you frequency. So if, therefore, I'll put here, or I can give you frequency F to be 10 gigahertz. I will not give you both. I will give you both if it is a microstrip line, all right? But this is an ideal transmission line, is in free space. And in free space, we know how much is the relationship between lambda and F. So I'm writing here where for an ideal transmission line, we have that F times lambda is the velocity of light in free space, which is 3 times 10 to the 10 centimeters per second. All right. So that's why I will not give both of them. So I can give you F or I can give you lambda. Then what else do I give you? I give you that R, say it's 100 ohms. And I give you that C. Let me see, I'll give you a number for C. Let me see, assume that C is 5 picofarads, all right? And now the problem says find a matching network that includes a matching network. In fact, what I will say to explain, so what I'm saying, therefore, find an appropriate stub of length D, okay, at some position, at an appropriate position, not any, but at an appropriate position, at a distance oops, sorry, it's not the one I had in mind. L sub s from the load. So practically, I want you to find D and L sub s, all right? Now, in all of these problems, we will assume that the characteristic impedance of the stub is Z naught equal to 50 ohms. Okay, that is a matching problem. And that's probably, with all of the detail that I included here, how I'm going to give it to you. All right, in this particular, so now we have this is problem, part A, part of the problem. Okay, so for this one now, as I told you, this is a problem which is connected. So part A, B, or C, but I'm not going to give you connected problems in the midterm, and I'm not going to give you as many, obviously, so you have less time than we have today, and they are going to be disconnected one from the other, so if you make a mistake in one, it does not propagate, all right, as I said before. So let's try to solve here this problem. Solution, rather. Oops, solution. Okay, for the solution, before we decide what to do, all right, step one. Step one in the solution, first of all, let me bring the picture here next to me. So my advice when you solve problems is always to have a graph, because I know you write on multiple pages. Put a graph on a problem on a separate page, or keep it, if you are doing it electronically, bring it wherever you do solutions, so you have it there in front of you instead of trying to remember. All right, so the most important thing I have to do is practically, and the first thing is to find ZL. All right. Now, what do I find here? Here I have two components that are in shunt. And that implies that the easiest way to go about this problem is not necessarily to work with ZL, but with YL. And why is that? Because the R and C are connected in parallel. If R and C were connected in series, I would have selected ZL to work with. All right, so now I work with YL because I write here shunt to remember that R and C are in shunt configuration. Okay, so how much is YL? So first of all, step one, small a, find YL. And YL is going to be the parallel combination of R, but not R. I mean, the parallel combination of two of a reactance and a conductance is a sum. All right, the parallel combination of a conductance and a reactance is a sum. What that implies is if I have a conductance, G, and I have a C, all right, that we know that in this particular case, YL will be G plus j omega c. However, here I have given you r. And what is g? G is 1 over r. All right? So practically, your YL is going to be 1 over r plus j omega c. All right? Because of this one here. So I will put this in a different color so you know that it's like a parenthesis. All right? This is a parenthesis, so we remember. So then, as a result, from here, what do we have? We know that YL is going to be, how much is R? R is going to be 1 over 100 plus J 2 pi FC. Let's see how much is 2 pi FC. 2 pi FC is going to be 2 pi F is 10 to the 9, to the 10, because it's 10 gigahertz. F to the 10. If I had given you only lambda, then you would have to calculate F. All right? Because when you have a capacitance or an inductance, you need to multiply those by omega to be able to find the reactances. Okay, now we know it. So here's going to be 2 pi 10 to the 10 hertz, all right, for the frequency. So frequency is in hertz. And times C, which is 5, 10 to minus 12. I have to make it higher, so that I'll make that 15. Okay, so 15, just to be a decent number. 2 pi 10 to the 10th, 15, 10 to minus 12, and therefore, this is going to be, no, I'll keep it, I apologize, I will keep it 10. I'll keep it 5, okay, 5 was a good number. I'm trying to find an easy number here. Okay, 5, so it's gonna be 10 pi, 10 to minus 12, and that is gonna be 1 over ohm. All right, at the end, because you remember this one was picofarads, therefore 10 to minus 12 makes it farads, and farads times hertz makes it 1 over ohm. All right, so now I have, since I found that, I have to go, well, no.
Professor,
Yes.
not be to the -2.
Yes, exactly, thank you. So now, thank you. I'm going to make this pi divided by 10, 1 over ohm, which in fact is going to be 0.316. All right, still a small number, but that's okay. 1 over ohm. All right, so now I'm gonna sum the two, and I have y sub l is 0.01, that's the 1 over 100, plus j 0.31, okay, and all of that is in 1 over ohm. So now we have YL. Okay, now what, now that I have found YL, it tells me that I need to, what I need to do is to then find a matching network, and the matching network, it has to be, it's rather a stub, nothing else but a stub on this transmission line, and I have to find a matching network to be able to match this load to the source at that particular frequency of 10 gigahertz. Okay, so now I will go to the Smith chart. In fact, therefore, I'm going to go and get a copy of the Smith chart. Okay, get a copy of that, copy. And we're going to go to our problem. And paste it here. Okay, it's a little big, so we'll paste it below. All right, let's see. All right. Now, we have therefore to go to the Smith chart to find the problem. And what we need to do before we go to the Smith chart is what? Can we go to the Smith chart with YL or ZL for another problem?
We have to normalize first.
Exactly. You will have to normalize. So B, we normalize Y sub L. How do we normalize Y sub L? What do we divide it by? Not with an impedance. We are going to divide it by the admittance. So to normalize, that implies we have to find this, which is YL divided by Y naught. And what is Y naught? Nothing else but 1 over Z naught. Okay? How much is Z naught? Z naught is 50 ohms, all right? So it's 1 over 50. Now, just to, of course, if you have a calculator and it's easy to use it, you can do an inverse of the 50, and then you go and divide YL by the inverse of 50. But you know what I was thinking in my mind, if I assume that I don't have I don't want to use a calculator yet, I'm saying, okay, since I have to find YL, which is normalized YL, which is YL divided by Y naught, practically I will have to take 0.01 plus J 0.31 and divide it by 1 over 50, which is nothing else but multiplying the original YL by 50. All right, so that is. So I'm not gonna inverse 50. I'm not gonna find 1 over 50 because then it's gonna make it easier for me. So now what I find from here is that the normalized YL is equal to 50 times 0.01 plus J50 times 0.31. And of course, since I normalized it, this is a pure number, complex number. And from here I have that YL is going to be 0.5, all right, plus J, and that's going to be 30 times. So 1.5, 15, I think. Am I right?
I think
It's going to be
maybe
150. Let me see, make sure I'm okay. 1 second. So it's 50 times 0.31. 50 times 0.31 equals. Then the other one should be 50 times 0.01 equals 0.5. Okay. So 0.5 here. Okay. So that is the normalized Isabel. Now I got that. Now I need to think what the problem is asking me so I know exactly how to go about it. All right, what the problem is asking me, let's go back. You should always read carefully the problem. Say, find a matching network, so an appropriate stub. Why do I say appropriate stub? Because the stub can be in series or shunt. It can, according to the design, it can be open or short, all right? So that's number one. Number two, it says, at an appropriate position, distance L sub S from the load, which means I have to find a stub, and I will take that to be a little further closer. So I'm going to take now this again, copy it, and put it closer here, paste. And now I'm going to draw. Now I will get rid of this. I will remove that. And now in its place, I will put Y sub L, normalize. Okay, Y sub L here. And if I normalize that, of course, I have to normalize anything eventually. And now what the problem is telling me is to go and place a stub. Since I have to place a stub somewhere, the stub will have to be in a distance less than L from the load, all right? So the stub, for example, it will be, well, it will be a shunt stub, and I will explain why when we start the solution. But it has to be in a distance from the load. So let me do this. It look like this. I don't know yet what I'm going to have at the end. That is going to come as part of my solution. So I will put here for this a question mark, because I don't know yet what it is. And the only thing I want to make sure is that this L sub S does not exceed L. Because if it exceeds L, then it's like the stub is going to go beyond the source, all right? If L sub S is larger than L. So the concern that I have here is to make sure that L sub S is less than L. That is important to keep in mind. Second, why would a stub be in shunt? To see that, you will have to remember how we will solve the problem on the Smith chart. So let's go and place, first of all, Y sub L. So what we have to do as part C here, so we'll have to place Y sub L on the Smith chart. All right. So now let's try to do this. What is the real part? Remember, you can use the Smith chart only for impedances or only for admittances. All right. Yes, you can go from impedances to admittances, but since we have not spent as much time with the Smith chart to make us really experts, I suggest on the same problem, you don't switch from an impedance to admittance in the middle of the solution on the Smith chart. You stick with only one. Impedances or admittances, only one. That's my advice. Not that you cannot do it, you can, but if you're not very, proficient with the Smith chart, you can make a mistake easily. So in my case, I'm gonna stick with the Y sub L. Y sub L has a real part. I'm gonna 0.05. Where do we put the real? The real parts go on this. So I will find 0.05. They go on these circles that you will see here that have their center on the horizontal axis of the Smith chart. And then they are tangential to the right side, okay, here. All of them are tangential to each other at the same point here. Okay, now, another thing, this is the real part of Weissabel. I'm gonna put it here so you can see it. This is the real part of Weissabel. So I'm gonna say here real of Weissabel normalized, and it's 0.5. Now, the imaginary part, okay, of Weissabel is, let me see here, 15. So obviously 15 is a very high number, and to find 15, I have to look around the periphery. Like I will have, let me use green for that, I will have to look around here and see at what point I'm gonna get 15. And I have to go all the way down here. And to find 15, this is 10, 10, 20, 15 is gonna be somewhere here. All right, so, well, because the number I gave you brought me there. When I give you the midterm, the number is gonna be designed to bring you more into the center of the Smith chart. But in any case, so now I found this circle. Okay, you see that? This circle here, which corresponds to 15. Okay, and that is the imaginary part So that's imaginary part. Trying to imaginary part of YL normalized. Okay, and then the intersection between the green and the red, so this one here, gives me the normalized Y-Sabel. So this one here gives me Y-Sabel. So that is the first step on the Smith chart. All right, so now, where do I want to go from there? I want to go to, and in fact, you know what? I have to go back a little bit and correct the numbers because I want to be, otherwise going to be so cramped on the periphery that you're not going to be able to see. So now that we see where it's coming, let me give you a slightly different number for C. So the best thing is to put here on 1.5 or 1. Okay, I will give you for C a different number. So to put it from 15 to 5, and then from 15 to 1, I need to divide 5 by 15. Let me see. Okay. 5 divided by 15. 0.3. Okay, so let me give you here 0.3. All right. So the only thing to do is to just change 0.3. Okay, so I will put here instead of this one, 0.3. All right, everything else is going to remain the same. Only then it's going to make it 0.6 pi. 0.6 pi. Okay, and then, so that is gonna, now I have to use my calculator. All right, so it's gonna be pi divided by 100 multiplied by 0.6. Okay, it's gonna make it 1.019. So it's gonna make it 0.019 approximately. Okay, so it makes it a lot smaller. And that is gonna fix the problem of not being cramped so much out at the perimetry of the Smith chart. So this is gonna be 0.019, okay? And then we normalize YL with the Y naught, and then here that is gonna be 0.019. And then of course here is gonna be 0.019. 0.19, and then here is going to be point up. This is approximately twice, so it's going to be 1. All right, so we got very close to 1 here, which is good. All right, I assume that 0.0, I assume that this one is 0.02 practically. Okay, so that is better because now I don't have to be that. Yes. Any questions?
Why did you change it to 0.019?
Because, you know, if I gave a 5 picofarads,
Right.
and that made the reactive part of YL very large. And when the reactive part of YL becomes very large, then you tend to be on almost, that implies that your YL is almost, has such a big reactive part that is almost reactive.
Right.
That's what I'm saying. So, and then all of the circles will be crammed together. So now I want to move more into the center of the Smith chart. That's the easiest thing for you. I would not care if they would give it to me as a problem. I would keep solving it. But now that I would like to demonstrate to you how to do that, it's better to be at the center of the Smith chart. So you don't get confused with circles that seem to be one on top of the other. See what I'm saying?
Yeah.
Okay. Yeah, that's why I changed it. All right. So, and when I give you the homework, I'll make sure that the same thing, the midterm, I'll make sure that the same thing happens, that you are not, that close to the outside of the Smith chart, to the perimeter of the Smith chart. I'll make sure that you're somewhere in the middle.
Is there a certain side of the circle we should start counting from?
What do you mean exactly? Could you repeat?
Like, does it go from like 0 to 20 on the other side of it, like the bottom half of the circle as well, or? Like I remember you saying before, like one side is a short, one side's open. It's like we should start from the correct one.
Here, this is, we are gonna find, this is the real part of Y sub L. Is that, that's fixed, all right? This is, as I said before, here, the real part of Y sub L. You see it down here? So that's the circle. Is that anything to do with this circle or the other one?
No, I'm asking about the reactive part.
Which one?
The reactive part of Y sub
I
L.
cannot hear you very well, so you may want to speak out a little louder.
I'm asking about like the reactive part.
Yes.
Of Y sub L. Well, there's a 1 at the top and there's a 1 at the bottom. So which one do we?
Okay. Well, because the top is positive, the bottom is negative. Okay. So since Y sub L now has a positive, a plus J1, we are gonna look at the top. Okay. And remember, we are using this for admittances only. All right. I don't have impedances. When you mix things, then it becomes tricky of where is plus and where is minus. But if you are only of one type or only of admittances and only of only of impedances, then you can stick with positive 1 up negative, 1 down, or negative values down, positive values up. However, that implies that you stick with one type. So now I'm sticking with admittances, and therefore for me, positive is up. Okay?
So if it's reactance, and
You
it's
can
opposite.
assume the same thing if you
Or-
stick only with impedances. Yes, tell me, go ahead.
So like if it's impedance, it's opposite.
No, if it's only impedances, it's still the same. However, if you have impedances and admittances together, then you have to have only plus for one, and then for the other, it's going to be the opposite.
Okay.
That's why I'm asking you not to mix them up.
Okay. So the numbers on the bottom, they're negative, but they just don't say negative. They just say the numerical value.
Yeah, it's a numerical value, exactly. And since we are using only admittances, then we can use positive up, negative down. If you were using only impedances, you can still do the same. All right? That's why I ask you not to mix impedances and admittances on this next chart. Unless in the very early, when some people, I'm giving you the impedance, Isabel, but then you have to use admittances, and only instead of inverting Isabel, you go to the Smith chart and you go to admittances. Only in the beginning you do that. But for these problems I'm giving you, stick with only the same type of loads, all right? Either admittances or impedances, but don't mix them up. And if you use them, if you use only the same type, then positive is up always, negative is down, okay? That's the rule for reactances. All right, so positive 1, for us, we're using admittances. Positive, therefore, 1 is up here, and I'm gonna use a green to see which one is the circle. Let me use a little thicker line. So you can see, this is the circle that corresponds to all the reactive normalized parts, which are 1, all right? And the intersection of the two here gives me my normalized admittance. So here, and I will put here, that's my normalized admittance. And to remember, is 0.5 plus J1, right? Now, I want to put a stub somewhere, but remind me at the end of the day, after I have the stub, what kind of an impedance if I were to look after I finish my matching, and I look now, let's assume that I call this, okay, remember I have AA prime, BB prime here, and then let me call this C prime. Now, after I'm done with the matching, the stub, and I have figured out everything, then I want to make sure that the input impedance here is how much to have a perfect.
Reactive.
How much it's going to be to have a perfect match after to the left of the stub. How much this Z input has to be.
Should it be the conjugate of the source?
50
Yes, but the
ohms.
source is real. So is Z not.
So it should be 50 ohms, right?
So how much should it be?
Isn't it the same as the reactive of the load, except the opposite sign to cancel it out?
No, I'm not talking about the stub. I'm talking about the total input impedance as I see it from the line.
Should be 50 ohms, right?
Yes, exactly. See, I'm not talking about the stub. We'll come to this. I'm talking about after I have designed the stub and everything is in place, how much should this input impedance is the impedance I see, is the impedance I see to the right of this arrow here. All right, if I am an observer at this point and I look to this direction, if I look like, okay, well, everything, okay, if I assume that this is, now all of my space, the input impedance that this whole thing presents to me to have a perfect match should be equal to Z0. Do you agree?
Yeah, that makes sense.
Okay. Okay, if I were to normalize these two, in fact, the other, instead, since I'm working for admittances, I can restate this. I can restate it and I say, instead of talking in terms of impedances, let me talk in terms of admittances. So practically, when I look towards that direction, my total input admittance has to be equal to what? To 1 over Z0. Do you agree? Why not? Why is that? Because Y input at CC prime is 1 over Z input at CC prime. All right? Is that clear?
I have a question.
Yes.
So y or like Zn at point CC, does the amount of transmission line like after that point affect its value?
What do you think? Let's talk about that. Who would like, maybe somebody else who would like to respond to this question? What do you guys think? It's a good question, but let's think about it. So if at this point on my line, let me use, this is a new, okay, I'm sitting there. If at this point on this reference line, my input impedance is Z0, then what happens to does the rest of the line have any influence on the matching? In fact, to solve this question, let me I'll put a page here and then we can remove it if you want. So I will keep this here for a moment and ask you this problem. If I have a transmission line like this, and at the end, I have a 50 ohm, and I have here Z0, and I have here Z0. How much is the reflection coefficient at this point?
0.
0. If the reflection coefficient is 0 there, how much is the reflection coefficient here?
It's not 0.
It is 0. Why is that? Because if you have a transmission line that has a characteristic impedance of Z0, then the input impedance at any point on the line, any point, the input impedance is Z0. And if the input impedance at this point is Z0, that implies the reflection coefficient at any point along the line is 0. There is another way to say that. If we have a transmission line like that, Okay, so another way to say exactly the same thing, it will be the following. I have a transmission line. Okay, and then I have a Z naught, oops, Z naught. All right, and then here, so the Z naught characteristic impedance on the line. The reflection coefficient is gamma. And then if you remember when we talked about transmission lines, we had the Z axis and we assumed here was Z equals 0. And we assumed here Z equals L, all right? And then we found that at any point on this line, let's assume at this point here, and let's assume that this point is D, okay, from the load. Gamma at that point at Z equals, okay, let me call this D and this D prime, okay. Gamma at Z equals D, let me call it the other way around. At Z equals D, all right, at this point, will be equal to gamma at Z equals L, all right, E to the minus J to beta D prime. Even if you don't remember this, what you should remember from this formula is that on any transmission line, the magnitude of gamma remains the same. On any transmission line, the magnitude of gamma is equal to the magnitude of gamma at the load, all right, for every Z, which implies that if your reflection coefficient at the load is 0 or anywhere else is 0, then the reflection coefficient is 0 everywhere on the line. Do you remember when we were discussing that on transmission lines? It was very early in this class. That the magnitude of the reflection coefficient remains constant everywhere on a transmission line, unless there is some kind of a stub that is added, some kind of another load that is added that changes. But if the line does not have any loads, any stubs, the magnitude of the reflection coefficient is the same. So talking now about this section of the line. Between the stub and the source, the section of the line does not have anything. No loads, no other stubs, nothing, all right? So on that section of the line that I am highlighting there, the magnitude of the reflection coefficient is 0. Therefore, if I make the magnitude of the reflection coefficient along this, at that reference point, that the magnitude of the reflection coefficient is going to be 0 everywhere else on the line here. All right? Did you get that?
Yes, ma'am.
Okay. Now, if this is then correct, if this is right in your mind, if you feel comfortable about that, then, so I will probably leave this here because I would like to put everything, maybe other students have the same question. Okay, so then what I will do is thinking that this, now because of that, therefore, because of the above, let me write it also here, because of the above, if this one, Y input at CC prime input at C prime is equal to Y naught, which is the inverse of the characteristic impedance, then practically everywhere on this section of the line, your reflection coefficient is going to be 0. There is a perfect match. There is a perfect match whether my load as an admittance is equal to Y naught, or whether my load as an impedance equals to Z naught. All right. In any of these two cases, the reflection coefficient is 0. All right. Because of that, therefore, we have this condition. If we do this, then the reflection coefficient everywhere to the left of C prime will be 0. All right. Because of that, what is the result of this? If this gamma is 0, all right, that implies that the input impedance here in this line, as I showed it, let's put this one here. The input impedance here is going to be equal to the input impedance to the, excuse me, the characteristic impedance of the line. And because this is the same with the source impedance, that implies that if this condition here exists, that implies that my input impedance here is going to be Z naught, and therefore, under these circumstances, I will have a perfect match to the load here. All right, that's what it implies. So in fact, I can write here that Z in at A prime, if this equals to Z naught, or this one is equivalent to this one, all right, because there is nothing on the line, all right, there's in between the two, and the reflection coefficient is going to be 0 everywhere. Okay, why am I saying all of this? Why do I pay attention? Because after the stub, where do I need to have my input admittance normalized? This is my input admittance. Remember, we want the input admittance here to be Y naught. And therefore, we want the normalized input impedance there to be what? That, what does that imply? This implies here that my normalized input impedance at CC prime is going to be what? 1. Do you agree? So I would like from here on the Smith chart now, as I move from here to here, I want to find my input impedance from this point, which is the load. I'm starting, you remember, I'm starting with the load, which is here. And at the end, I want to find myself where? Here. I want to make sure that this is the place where I'm going to end up after I put the stub. Okay, I want to end up here after I put the stub. So that's going to be my Y input at C prime normalized according to before, all right? According to this. So I want to be at the center of the Smith chart. Okay, now to remind you, let's go back to some things we've seen before. When I am here, YL, for this part of the transmission line, this part of the transmission line has a reflection coefficient. And to move from BB prime, which is here, all right, to move along this direction of the line, all right, so I want to move practically, let me show it here. I want to move from here there on the Smith chart. How am I going to be able to move along that direction? On which circle? You remember on the Smith chart, I can only move on circles. I cannot move on straight lines. I cannot go from here there. It's forbidden, right? Cannot do that. So which circle am I going to move along? The constant gamma circle, which is the circle of the transmission line. You remember that circle we were doing when we did matching circuits? That is the one. Okay? This is the circle of the transmission line. I'll do it here. This section of the transmission line, this small section of the transmission line, and I will do this one in purple so you can see. Okay, for this small section of the transmission line, this is the circle. Any point on this section of the transmission line of the purple there is on this circle. This is a circle that goes through the center of the Smith chart and it goes through the load. Any questions?
Yeah. Because just right before you made your last sentence, I was gonna ask, like, is there a radius for this? But it just has to go through the
Point, the load.
like, through the load, and then has to be centralized.
Yes,
Okay.
exactly. And that's it. That's the radius. All right. Yeah. So then you do it. I mean, the radius, as we said, is this one. For this circle, this one. That's your radius. But you cannot move along the radius, all right? You can only move along the circle. That's why I erased that, because I don't want anybody to believe that they can move straight. Now, so from YL, I can move. So when I go, however, the Smith chart always tells us which direction to do things. So I go from here. Let me back to this here. I move from my load. Let me do this. I move from my load like this. And I want to find a point to stop where I'm going to put the stub. All right. So that's the question, where is going to be my point to stop? Now, how are we going to do that? The following way. We are going to go to the Smith chart. And first of all, we move from the load towards the generator. So here you have to pay attention to this one. The Smith chart, if you go here and says wavelengths toward generator. You see that? And shows, in fact, let me clean it up so you can see it. It says exactly wavelengths here towards generator, and it has an arrow. All right, that means that to find that point where I will place the stub, I need to move clockwise from where I am. So since I am here at this point, All right, that's my load. I can only move this way. All right, see the arrow, I can only move this way. Okay, that's one good thing. At least I know which direction I can go. The question is, where am I going to stop? Okay, so let's think about where we are going to stop. Am I going to stop here, 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 here? All of these possibilities. The answer is no. There are only 2 places where we can stop. Okay, let's think why. Let's go back to this and then look at the stub. The stub, when you place the stub, in essence, you place in at CC prime, what? A shunt load. So practically, if I were for a moment to put this is one parenthesis and create another one. All right, so let me drive a line here. Okay, as a parenthesis, let me take this example, copy, put it down here. Okay, and what I will do is the following. When I place a stub, in reality, I place a shunt load. Okay, so now let me take the stub away for a second. And do this. Okay, I put away and then I'll put it back here. Okay, I took the stub away for a second. Now, in its place, what kind of a load am I gonna have at CC prime? What kind of a load at CC prime the stub is creating? Is it a real load? Is it a reactive load? Is it a complex load? What is it? Who can tell me?
Both.
Yes, Robert.
Is it both? Like reactive and real?
What do we call, to answer this question, let's ask, what do we call a stub? What is a stub? Here I put a question mark at the end of it. A stub, by definition, is it's a section of a line, so stub here. A stub is a section of a line that has what at the end, by definition? What is the load at the end of this line? Is either a short, and we call that the shorted, short-circuited rather, short-circuited, or what? Or an open. Another possibility for the stub, duplicate, will be to be open. If it is open here, okay? But a short-circuited and an open-circuited stub from transmission lines, what kind of input impedances do they give? Let's think about this. This is, in fact, I will give this a different color, so we separate things easier visually. This one, okay. So what is the input if this is CC prime? C prime, and this is CC prime. How much is, according to what we've seen, how much is the input impedance or admittance here? So let me call that Y S of the stub at CC prime. All right, this is the admittance of the stub at CC prime, and the same thing here. ys at cc prime. What do we know from theory? We know that the impedance that we have found in the book and from 332 practically, that this, to find ys, cc prime and ys in both cases, you practically have two formulas. All right, so zs cc prime for a shorted circuit stub. All right, so let me put this red here. Let me move this 1 second. Move this to the center. So this one, for a short circuited stub, this is equal to J Z naught, because that's what I have given you, that the stub has a characteristic impedance of Z naught tangent beta D, where D is the length of the stub. All right. And therefore, I mean, if this is that is impedance, then ys cc prime is going to be minus j y naught, the inverse of the zs, cotangent of beta d.
So
Okay.
that's the formula for like
Yeah,
both types of stubs.
this is the formula for the short circuited, the red, and the formula for the open is zs at c prime is minus j z naught cotangent beta d. Let me move it a little further out. And therefore, ys at cc prime will be j y naught tangent of beta d for open and for short. Okay? For these two cases. So,
And is D the distance from the load?
no, this is the length of the stub.
Oh, sorry.
Yeah, here.
But okay.
So, what does these formulas tell us? That the load that is presented by a stub, whether it's open or short, is what? Is it real? Is it imaginary? Or is it complex?
It's imaginary.
It is imaginary. Perfect. Okay. This is important to remember, right? And therefore, that tells me that I can only stop, all right, at a place where, since that implies what? That if my stub that was here, I had the stub here, remember, let me put it back. I had the stub here and here, all right, make it short a little bit because I don't have that much space anymore. It was like this. If I place a stub there, the only thing the stub can do in parallel is to add a reactive load. So practically I can take the stub out now and put a reactive load in there. All right, I can put a reactive load. And because it's a shunt stub, I will put the reactive load in the form of an admittance. You agree? All right. Okay, so now I know that this ys is only reactive. So, and this one here is reactive, which means my Y input at CC prime is going to affect only the reactive part of whatever impedance I had right here, whatever impedance I had at this point. All right? Because practically when I move YL, remember, YL is here. YL is this point. All right? And I can move on the purple circle only. But wherever I stop, I have to make sure that the real part of normalized YL is equal to 1, meaning that the real part of YL is equal to Y naught. All right? Because wherever it goes after I move. Because I want eventually, so when I come here, you will see when I come at this point, then I know that my real part of that point, and let me see, that is gonna be, if I go here, all right, and I expand the view, this one, let me here clean this up. You have it up previously, all right? So I'm not gonna have all of these details because it becomes too crowded. So at that point, if I were to look for the input impedance to the line now, all right, to the line. See, I don't say stub, I don't have an S there. So it's CC prime. At that point is before, is right to the, is exactly at the right of the stub. That one, and is gonna be related, all right? So let me call it to the right, I call this plus, and to the left, I call this minus, you know, just to differentiate because we are right at the same junction. So there is a single relationship that connects this one with this one. And what is this relationship that connects the two? The relationship is, and in fact, I want to keep that. The relationship that connects the two is that, I'll put it here, that Y input at CC prime to the left of the stub is equal to Y, the stub at CC prime, plus the Y input to the right at CC prime. Okay, this is the relationship that I have at CC prime. Okay, that's what happens right there. As I look towards the load, I see a total admittance, okay, at that point, which is the admittance of the stub plus the admittance of the line after the stub, the purple one here. So these two, since I want this one here to be 1. Do you see normalized? I want, however, according to these two relationships, I want this one to be Y naught. Okay? And therefore, that implies that my normalized impedance here, which I call left, all right, is equal to 1. That's what I have. Therefore, I can only stop here where this line, the resistive part circle that has a real part of 1, takes me. Okay. So I need to be on this circle. And let me also show it better here. I need to be here. Let me see. I need to be on this circle. This is the circle where all the points of this circle have a normalized real part of 1. So, and in fact, I make it a little thinner. Okay, so I'm gonna be on this circle. And from, therefore, the arrows that I showed, there are 2 points that I can stop at. One is this point, let me see. This point here. One is that point I can stop. And the other is this point. All right, these are the 2 points that I can stop at. One is as I move from YL, all right? You remember the point I'm moving from is this point. That's my load. So as I move from the blue, light blue point to the red, that shows from blue to the red, it shows that I move along this part of the line. I move along this part of the line, okay? And then at red, I'm gonna be either at CC prime for a shortest section of line, all right? The one up here, that 1 point. Let me see, change one, at least one color. The green one is gonna give me a shorter length, the shortest distance. The red one is gonna give me a longer distance because I will have to continue then. I have to continue with this to be able to find the red point. So one gives me one distance, the other gives me the other. All right? Either one for us is acceptable. Any questions so far?
I have a quick question, just out of curiosity, what would happen if you, there's no reason you would do this, but if you went counterclockwise the other direction, what would happen in that situation?
It will give you, no, it's not for, it's forbidden.
Okay, gotcha. Just wanted to check.
Yeah.
Thank you.
Sure, it's forbidden.
Sorry, you said counterclockwise was for what?
If you go towards the load, but we never go towards the load here. So for us, for our problems here, we always move clockwise. That's what.
Thank you.
All right, not the opposite direction. The opposite direction is forbidden for us. It's like you go against, like in a highway. All the cars are going from one direction when they come back on the left. But if you go into the other direction, you're going to get killed. Think of that, all right? It's forbidden going to the opposite direction. It's like you go to the opposite lane, rather.
Duly noted.
Pardon me?
Duly noted.
Duly noted, thank you. All right, now, however, either the green or the red are possible solutions, okay? We are not ready to actively select one yet, because for us at this point, I give you access to either of the two. The only thing that you wanna make sure is this condition, that as you translate these dimensions, these directions to L sub base, you make sure that L sub S has to be less than L. Now, in this case, I have to tell you that I gave you a long enough L where this is not gonna be an issue, but, and I'm not gonna trick you or anything, all right? But in our case, either one of the two will be appropriate. But in any case, when you have a given L of your transmission line, then it's good to check. All right. So let's see. We'll take each one of these now. Points, let me call this point, the green one, I will call it C. And why do I call it C? Because, you know, that's exactly where this is the green C. Let me see, that's too thick. Here. Green C, and this is the red C. The red C. Okay. Now let's we'll check each case. In fact, in what I could have asked you is to give me the shortest possible length, to tell you the truth. If I had asked you in the problem to give me the shortest possible length, then from these two would have been C, the green C, all right? But let's see. I can probably ask you that so it makes it easier. All right, so I could have said here that I want distance L sub S from the load to be the shortest possible. Where I could put here as part, just to simplify things. I don't want you to check two solutions. Out where I will not give you, I will try to contain the problem so you don't have too many things to look after in that short period of time that you will have available. Where L sub S is as short as possible, is as short, okay, as possible. Let me move this a little bit.
I have a question.
Go ahead.
So the formulas for the impedance of like a stub,
Yes,
the only distance I see like in the formula is like the length of the stub.
yes.
How does where does the distance from the load come into play in that formula?
From
Or,
L
like,
sub S.
what does it affect?
L sub S here, the difference between L and L sub S is going to give you the distance from the, you mean the load, the distance, could you repeat? I'm sorry, because I may have heard you
I'm
wrong.
just so like the formula for impedance of the stub, it doesn't include L sub S.
No, because it's the impedance of the stub.
So
The,
then
the impedance, look at the stubs. When I look at the impedance of the stub, I don't care where it is located. The impedance Y sub S of the stub only is dependent on the stub itself. The impedance of the stub does not change when you place the stub in different locations, the impedance of the stub. What changes is this one. Why does this change? Because of this relationship. But this one does not change. This one does not change. Do you see that?
Yes, I believe so.
Okay.
Is it because, well,
L sub S has nothing to do with the stub itself.
so what about L sub S? Like, what is it changing? It's changing, you said.
L sub S changes this one. L sub S changes the impedance you see on this purple transmission line if you are right next to CC prime. That's what L sub S changes. All right, this is L sub S.
Okay. And what about it is it changing? Like what within the formula for YN at TC?
You don't see the formula, it shows here. point C. L sub S, you remember what we said? To go from the blue point here to C, to the green point, is one distance. And L sub S specifies the changes in L sub S, specifies that the impedance of that point of C has nothing to do with the stub yet. All right, we said we want to stop on this blue circle here. We want to stop on that. And when we stop on these, there are two places to stop at, C and C, green C, red C. The distance L sub S is going to be either the one that I show you here, from here, that's the distance equivalent, or from here all the way down here. Okay.
So which, so that's not length of the stub, that's L sub S?
No, the length, we have not gotten into the length of the stub yet.
Okay.
We only got it into the formula to show you that it was reactive. Okay.
But I guess I'm wondering, so if we're changing the, like the reactive part of it by normalizing it to, or going to the
Center.
or to the blue circle, wouldn't that be changing the reactive part? So they're like,
Yeah,
it would be changing the
I'll tell you how. Okay, so that's the next step. If we stop at C, at the green C, we are not at the center of the Smith chart yet. All right. So this one here shows only movement of the purple section. Okay, here. It does not show anything about the stub yet. What shows the impact of the stub is when we started moving along this direction to go to the center of the Smith chart. All right. To go to the center of the Smith chart, the impedance here, and I can write it as a matter of fact, approximately. This, the line that you see here on the green C is practically Y in at C prime plus. And the normalize this one according to that, it will be 1 plus the reactive component is 1.6. All right, if I read the real and the reactive components of the green dot, that green dot is nothing else but the normalized Y input at CC prime plus, which is this one. This is the green dot on Smith chart. And to go from this, the green dot, to the center of the chart, all right, because that's where I have perfect match with the rest of my line. So the center of the chart, let me call it, let me give it a different color. Also, what color? This one. That's kind of the center of the chart is this pink dot, and that is equal is this one. So to go from the green to the pink, I just added a stub. And here, to go from the green dot to the pink one, I just added a stub, and that addition of the stub shows, what color have I given the stub? Red. Okay, shows this. That is the change in the reactance that the stub causes. So now I have, look what I have done. This is, let me use the different color. So this is your y in C prime, left of the stub. That is equal to 1. So now, let me see. What we have said before is y input at C prime normalized is equal to y of the stub, which is red, ys of the stub at C prime plus the blue, which is y in the green, rather the green dot anyways, plus, okay, the other is negative, to the left of C prime, to the right of C prime, and that is then C prime. So we have said that. Now I'm gonna put things there. I know that this one is 1 normalized. I wrote it here at the center of the chart. The other one is 1 plus 1.6. So this is equal. And this one is 1 plus J 1.6. Did I put J there? I forgot a J. Well, so, okay. And then in between these two, I have ys at C prime. But now I can solve this equation. All right. This and this goes. And what do I have from here? That ys at C prime is minus J 1.6. That's what I found. See, that's where D, the length of the stub, comes when you move from C to the center of the chart, from green C to the center of the chart, which is the pink. All right, so now from that, I found this relationship. Okay, well, how good is that gonna do to me? The following. Now I'm gonna take a new copy of the Smith chart, because now I'm gonna use the Smith chart to find the length of the stub. All right, so I'm gonna take, we'll go to a new copy. So you can use the old one if you feel comfortable, but for me to clean it up a little bit. So copy here, and then I'm going and paste, and then I'm gonna clean this up from a number of things. So probably I will remove for a second what I will remove. Okay, here. Let's do it partially. I'm gonna remove this part here. Right, move this part. There. I'm gonna remove all of this circle, because I don't need it anymore. This one, and this one, okay? And then I'm gonna remove partially here, this one, and this one. So if you think, the only thing that I've done with all of these circles is to be able to go to the center of the chart, all right? Because I cannot go straight. Say the blue, this light blue here was my load. And I want it to come to the pink. But I cannot go straight. That's why I had to develop all of these circles, all right? So now you can see why I have to put all of this, but this is the movement on the Smith chart that I made. Okay, Now I can use the Smith chart. I can remove, this is the, okay, that was 1 minus, what did I do? I think it was plus, yeah, plus J. Here, plus J 1.6. Okay. Now I know that my Y sub S normalized is minus J 1.6, which means on this Smith chart, I will find minus down at the lower end. Minus J 1.6 reactive is here. And since I have the, let me do it with red, since I use that always for color, red, and this one, red. Okay, that's YS minus J 1.6. Okay, now we are using admittances. Okay, so I'm gonna ask you a question. And the question is gonna be, where on the Smith chart I have the admittance of an open-ended stub? How much is the admittance of a stub that is open-ended? The admittance.
Infinity.
Infinity is the impedance of an open end. So how much is the admittance of an open end?
0.
Yes. Okay. Where is 0 on this chart? Since we are using only admittances, 0 is here. Always, all right? We have not changed anything on the Smith chart because we are using exactly only Y's, only admittances, as we said very early. So that is 0. And 0 in admittance form, okay? Remember that 0 in admittance form means what? Means open circuit for admittance.
And would it be opposite if it were?
Yes, impedance, yes. Now, what is the admittance in a short-circuited stub at the end? What is the admittance of a short?
Impedance 0, admittance infinity.
Yes. A short gives us infinite admittance. So in admittance form, that's a short circuit in admittance form. Okay. All right. Now, always as practice, we would, again, that one here, the left side or the right side, will be the load of a stub, the end of the stub, open or short. If I am at the short, if I assume that my stub is short-circuited, then to find minus J 1.6 as input, I'm going again from the short, the end of the stub, towards the source. All right, so I will have to move around like this. Ah, that was too thick.
You still have to go clockwise at this point as well,
Yes,
right?
always clockwise. But I will have to move from there until I come to this point here. There. Okay. Now, to find the length of the stub, I do two things. I write a line from the center of the chart to this point. Okay. And then I write another line. This is the end of this is the point where the stub connects to the line. And practically I write another line that goes through the end of the stub. All right, and then I try to find what are the numbers I see. So here, this one is 0.25, okay? And this one is 0.338. The distance between these points, the distance between, oops. Okay, let me do it here. The distance like this is the length of the stub. This is D. How do I find D? D is, I will subtract from 0.338. I will subtract where I started, 0.25. And that is in lambda, which means that D then is going to be 8, 5 from 3, prime from 13 rather, is 8. Lambda. So I found from there that the length of the stub here is 0.088 lambda. Okay, that is one. The other thing that I have to find, oops, is the length of the line, L sub s. Okay, so I did one here, I found one. Now I have to find the other. You see, to find L sub s, to go along that distance, I moved from here, from the blue to the green. So again, to find that distance, I take one line and I connect it from the end to the blue. And then I take another line, which is the beginning where the load was, and I connect from the pink to the green. And I want to see now how far I moved to go from the blue distance, from the blue point to the green. And then I look here and there. Okay. And I found this point here. This point here is 0.134 lambda. And this point here is excuse me, 134. And this point, I think I covered it with the line, is 0.178. Okay, so this distance, which is L sub s, to find this distance, I need to subtract these 2 points. So then I have that L sub s equals 0.178 minus 0.134 lambda, or that gives me that L sub s equals 4.400 lambda. So now I found the 2 lengths that I needed. Okay, I took this much time to do this because I had to explain all steps in between. But when I want you to solve this problem, I don't want you to write all of this theory. These are things that we've done as part of learning, all right? I would like you, in fact, to, I don't need to know about the stubs, for example, the way I wrote it here. I don't need this much explanation here. I mean, I will assume that those things, you know them, all right? This is only to remind you today of all of these things. And then, so practically, all of this gave you two results. D here, copy, paste. Ah, okay. Anyways, D and Elsa Bess. Okay, so we'll write them here again, have them together, and that is the response to that question. But we did also practically a review, all right, of Smith charts and that matching. And Elsa Bess 0.044 lambda. Okay, so now you have these two. Was this clear the way we did the solution?
Yes.
Okay,
Yes,
I have a
ma'am.
question, though.
because then I will copy this and I will put it on Canvas. All right, to get together with the video. But I will do this first immediately because the video I have to edit it, so I will be able to do it later tonight. So, so that is one.
I have a-
Another, yes,
question. Whenever we were talking about like the open, like in terms of admittance, it's like the open is on the left and the short is on the right.
yes.
If it were impedance, would open be on the right and the short be on the left?
Yes.
Or would they stay on the same side? It's just the values we're talking about are opposite. Like,
No, if you use only impedances, impedances, all right? Then left will be 0 and that will be short, right will be infinite and will be open.
okay.
Okay.
Wait, so the right would be, okay, thank you. So the numbers like 0, infinity stay on their respective side.
Yes, they stand.
Okay.
That's what I told you, that it stands if you don't mix impedances and admittances. If you use only impedances, which I will use if you have anything, a stub in series, or if you use only admittances, where I would use if you have a shunt stub, then the numbers stand. They mean exactly the same, all right? I mean, 0 stands where 0 is, infinite stands where infinite is, positive stands where positive up, negative below. Those do not change. As long as you use only impedances or only admittances, all right?
Okay, thank you.
Okay. Now, another problem I would like to solve for this one is the following. Now that you know, even I said that the problems are connected, but I don't have to connect them. And as a matter of fact, what I will do with the midterm, I will give you an option to solve one problem or another. I'm not gonna give you only one problem and say solve that.
I
Right.
don't have a question. Does that mean we have only 2 questions for the midterm?
I will, it depends. I have not made the midterm. I will make it tomorrow. If I think the problem is going to take you longer, it's going to be one, but I will give you 2 problems to do one or another. All right.
Okay. And would there be multiple parts underneath, or is it just going to be comprehensive like this question?
Yeah, if it's comprehensive like this, it's going to be one, obviously, problem. If it's like simpler stuff to do, it may
Right.
be 1 or 2.
Okay.
All right. I will never give
Professor,
you, yes.
sorry. I assume we'll just bring Smith charts of our own to use, right?
I will have Smith charts online for you, and then if you come to class, I will have them in paper form also.
Okay, great. Thank you so much.
Sure. Okay, let me see what else. Okay. Here. Now, let's, if I were a different problem, I would say, okay, now I have the following circuit. Okay, I will take this now since we have designed it. Take this. That's a different problem now, right? It's not the same part of the same problem, but since I have the circuit, I'll take it. So let me take this copy. Okay. And now problem 2. Okay. Paste. You have this circuit. Let me clean it up a little bit because now we have designed, if I give you another one, of course, everything is going to be given to you. And so this is like this, that, here, here. Okay, then here, so obviously short here we found. Okay, and here, let me erase that part. Okay. Let me assume now that we have here is ZL. It does not matter. I will put YL. Oh, I'll put the same. I'll put an R. Okay, R and C. And then what did we have? Let me put the first ones, conditions. So take all of these, copy. Copy, paste. Okay. And then I also give you that, what did I say? L is 3 lambda over 2. And then I give you that L sub S is this. And L sub S, we found here 0.044. And D 0.088. And what else did and this one is in node 2. Okay. Now you have this circuit, and assume that what I have between AA prime and BB prime. So now I put A squared around it. Okay. And I call that a 2-port network. Okay, so practically I can go in there and I can call that a 2-port. So, and I want practically out of this 2-port to characterize it, not by putting down everything that I have inside, and graphically, but I want to characterize it by one network matrix. All right. Okay, let's assume that is this. And this is a 2-port network. Okay. This is to port. Okay, since that looks horrible. Okay, I remove that. So I want you, so what the problem says is number one, find the A, B, C, D matrix. Okay, then two, find the scattering matrix. I can ask you something else, all right? For example, let's assume that I ask you these two things. The ABCD matrix is the most important one. Now, how do we solve this? Here is what I'm going to do.
Could you go
Yes.
to the picture of the circuit real quick?
Oh, sorry. Yeah. So you have seen, as you see, I have excluded the source and I have excluded the load, but I have included everything else. So now this is my two port. And for that one, I will ask you to find, first of all, the ABCD matrix. All right. I'm gonna do that. So I'm gonna ask you to develop anything. Do you remember what I said? I don't want you to compute, to develop it like out of fundamental basics, but I want you just to tell me what it is. So how would I do this? Okay, so here, in previous example, I solved one case like that, but let me see. Okay, let me go to this somewhere else. No, right. Let me see here, filters. I need to find something that I just saw it somewhere. Let me see, introduction to filters. No. There is, if we go to our notes, and let me, I'll find it, 1 second. Wait, bear with me for a second because I just saw it. 1 second. No, that was today. There it is. Let me take a copy. Okay. Let me now go to our place. Here. All right, so here you have from the notes this table. Okay. Do you remember where this table is? In the text notes. Okay, let me see. Let me go, not this one here. I want you to be able to at least read the text notes that I give you, because there are things that you will find very useful there. And then that's why I put them also in the modules. So network theory. I have already removed a lot of pages. So what I want you to remember, if you go here, let me see. Also, that has a number of examples, but at least I want you to remember two things. Definitely the definitions of the matrices, but this one. This is a very important table, and I want you to have it, to know at least where to find, to have it available. And then from there, you can find expressions also. Let me go down 1 second. Here you can find how, in terms of S, let me see. Second. Here are the scattering matrices of simple networks. Here, conversion between S and ABCD matrix. It gives you the formulas. All right, so I asked you, this is also very similar to the homework we had recently. So I asked you to find the ABCD matrix, and then from there to find the scattering matrix. And these are the formulas you're going to use, all right? These ones here. The 2.208 and 2.209. All right. And then there is another formula that I would like you to remember. Kind of slow here. Oh, sorry, I went too far. Measurements that in the lab. Okay. Here that gives you the reflection, the input. Well, I'm not gonna ask you anything like that, but I would like you to also read the return loss. These are important things we need to cover later. All right, they're very important sections that you will need to read. So you can recognize these are 2 ports, all right, that we have seen. Look at 2.26. So for example, if I give you a 2-port and the scattering parameters, and then I give you a load at the end, this is a way to find the input reflection coefficient at the port. That we will see that later. I'm not going to ask you right now in the midterm to do anything like that, but these are important things we need to go through, that we are going to see them again for the rest of the class. But in any case, for now, what I want you to do is to remember the ABCD matrices of the ABCD matrices of simple networks, which is this table that you've seen, and the relationships that give you the scattering parameters from the ABCD matrix. That's what I want you to know, all right, to remember. So now, if we leave that and we go here, okay, so I carried that table with us. Let's look how to take this. What is this 2-port network? This 2-port network, practically, I will redo it here. Okay, I'm going to take a piece of it. I will take this piece of it, copy, place it here. Okay, and then I will clean it up a little bit. Don't need that. For the time being, I don't need this. All right, I don't need that. I don't need this. That's the network we have for which we want to find the ABCD matrix. All right. Here, this is Elizabeth. So let's see about how many parts this is made of. One is this transmission. So here, I will copy this and then I will also, I don't want to redo it, paste. Okay, first of all, is made out of this transmission line, the blue one. So let me take this one here and move it. I will make it shorter also because it's only the blue part. Okay, that's from, you remember these were C and C prime. All right, so this one, that is C, excuse me. That's C, C prime. Okay, then we have that section of line this, and then also that connects to CC prime. And then I have the stub that also connects to CC prime. All right, do you agree with how I split the three parts apart?
So we treat the two sides of the transmission line as separate?
Yes, because they have a stub in between.
Oh, okay, thank you.
Yeah, two sections. You split them, you consider them two separate sections, even if they have the same Z naught here. Okay, so now I have 3 two-port networks. Okay, I have, and let me call, in fact, because this is also a two-port, the stub, I will call it here. Let me give it some additional names. After now I split it, I will call it here D. All right, D prime, now that I did the split. So I'm not confused. E prime. And then here, F prime. So in fact, I will also, so I don't create. So this is C prime, and then everything else here, I'm including it red. Is that red? And everything else here. Okay. So now, and then everything else here, I have 3 different fundamental three different fundamental two ports. All right, so here I'll do this. All right, so let me call this 1, 2, 3. These are connected in series, and then if we know that if I find the ABCD matrix for 1, that's how I indicate it. And then I find the ABCD matrix for 2. And then I find the ABCD matrix for 3. then I know that the total ABCD matrix, total, is going to be the product of the three. 1 times 2 times 3. Do you know why I can do that? Can somebody explain to me why I can write this expression? Have you guys reviewed ABCD matrices? Okay, if I have a, so parenthesis here. If I have a 2-port, all right. Then assume here there is 1 voltage, V1, and the current that flows like that, I1. And then another voltage, V2, and a current that flows here, I2. Then ABCD matrix for this connects V1 and I1 with V2 and I2. All right. Now, if next to it, if next to it, I had another similar to it, but I would call those all primes, all right? What would I have? The same kind of relationship, copy, paste, but all of these will be different, all right? Prime, oops, excuse me. It will be prime here and prime there and prime here and there, and all of these will be a different matrix, obviously. However, if I connect these two, if I directly connect them, then what do I see? From Kirchhoff's law, all right, I have that here, that I2 equals with I1 prime, and V2 is equal with V1 prime. Which means then that I can rewrite this one to be V2 I2 equal to A prime, B prime, C prime, D prime, V2 prime, I2 prime. That implies that I can take this part here and I can replace this by that. So from these two, I can write that V1 I1 is nothing else but A, B, C, D times A prime, B prime, C prime, and D prime, V2 prime, I2 prime. That tells me, therefore, that if I connect two networks like this, with this direction of the currents, if I connect two networks that each one of them has an ABCD matrix, if I connect them like serially like that, then the product of their ABCD matrices gives the ABCD matrix of the total network, all right? Therefore, I can go here and find the ABCD matrices of these three parts, 1, 2, and 3, and then plug in there and find the total ABCD matrix. So let's try to do that. All right, so I'm gonna take this one first, copy, All right, and then, so I have A, B, C, D, all one. The first one is a section of a transmission line. So I look at this. Where is a section of a transmission line? Here. All right, that shows a section of a transmission line. However, before I plug in there, or the whole thing, let me write it down and then I will simplify it. So that is for the section of line. Okay, part A.1. Is that how? Yeah, part A.1. That is then let me see one section. Okay, it's cosine beta L, J sine, okay. So correct me if I make a mistake, beta. But then I will call that L1 because the L of the line here, this one, which is L1, this L1 is L minus L sub S. You know, it's not a full line from the beginning. That's why. So I will call it like that. And then I have J Z naught sine beta L1. I have J Y naught sine beta L1. And then I have a cosine. Am I correct? Beta L1. Let me see. Yes. So I'm correct here. Now, before I try to put the other matrices, I need to plug in beta L1. First of all, which is 2 pi lambda. And then how much is L1? Is L, which is 3 lambda over 2 minus L sub S. And L sub S was 0.044. Okay, minus 0.044 lambda, which made it 2 pi lambda, and then it's 1.5 minus 0.044 lambda. Let's see. 1.5 minus 0.044 is 2 pi lambda times 1.456 lambda. This and this goes. And then that gives us 1.456 times 2. 1.456 times 2. And that is times pi equal, and in rads, this is 9.152 rads. And then after that, I'm going to go and find the cosine of this, which is minus 0.963, and the sine of this, so I have 9.152, and then sine of this, which is 0.269. Okay, and then I have Z naught, which is 50 ohms, and Y naught, which is 1 over 50, 0.02, 1 over ohm. Okay, so now what do I find? I find that ABCD CD 1 equal to minus 0.963 J 50.269 times 50, let's say 13.45, and then they have 0.269 divided by 50. That makes it J 0.0054, and then we have minus 0.963. That's how we found the first matrix. Then we go to the table and we find the matrix for a shorted stub, which is here. The matrix for shorted stub is 1, 0 minus J over Z naught tangent beta D. So it's going to be this is going to be 1, 0, 1 minus J, and then divided, make Z naught tangent theta, where theta for the stub is beta D. So now we have D, so beta is 2 pi over lambda. D is 0.088 lambda. So that is equal to 2 times pi times 0.088, and that is going to give us a 0.553 rads. Well, I hope so, maybe not. Let me see, I may have missed something. 2 times 0.088, yeah, times pi. Yeah, I'm correct. Which means tangent of that is going to be, tangent of this is going to be 0.6171. And therefore, the we are going to have that A, B, C, D, 2 is going to be 1, 0, and then minus J, and then we have 1 divided there, divided by 50, equal divided by 0.6171 equals, and that makes it 0.021. Okay, and the last one is the other section of a line. Now to find that, which is the same as above, let me rewrite it, is cosine beta LS J Z naught sine beta LS J Y naught sine beta LS and cosine beta LS. Yes, and then, so beta LS is 2 pi over lambda times 0.044 lambda, which is 2 times pi times 0.044 equals in rads 0.276 rads, which makes the cosine of that to be 0.96, and we have 0.276 rads sine of this to be 0.272, and then it makes our A, B, C, and D three to be 0.96, J 50 times 0.272, 13.6, and then we have 0.272 divided by 50. We have J 0.0054 and then 0.96. Okay, and then so you have these three matrices, 1, 2, and 3. And then multiply them. But when you multiply them, you have to keep the order. So first, I would multiply A, B, C, D 2 times A, B, C, D 3. All right, and then that would give you this one, the first one, times this one, and that will be 0.96. And then this one times, excuse me, yeah, this one times this one, which would make it J 13.6. And then you would do this one times this one. You multiply, you find the values, all right? And then after you find that, then you multiply A, B, C, D 1 with whatever matrix you have found here with this one. All right, so just to show it. So you put this, let me see. This one here, you put it here and you find the result. Now, in this particular case, you can find, in fact, the total ABCD matrix. And from there, and of course, you find it for the design frequency, all right? Because there is no frequency there, only there you can find it. And from there, you can find the scattering parameters, as I showed you in the book if you want, or you can find other things. But practically, I think if I were to give you something on this specifically, I will give you either some definitions, what is ABCD matrix, what is scattering matrix, what is admittance matrix, what is impedance matrix, so the definitions of the matrices you need to remember, and maybe how you find an ABCD matrix from a circuit that I will give you. So you split it, you simplify it down into specific components, and then you multiply, you compute the matrices, since I will give you exact dimensions, and then you multiply them. But it's the fundamental thing is to know the definition of the matrices, and what we talked about, the scattering matrix, how we define it, the fact that a reciprocal, passive circuits, all of these S12 and S21 are identical, these kinds of things, the properties of the scattering matrices. And I think so tomorrow, practically, we are going to work more on scattering, on matrices rather. But these are the two possibilities I can give you. Matching, I will give you probably two problems with questions to select from. That's what I think I'm going to do. One on matching networks and Some will see, but they will be, I will give you some, the ability to select something. So not just one problem. Do you have any other questions?
Yeah, I have a question.
Yes.
So on both problems, so you said when it's like for the loads, when it's a negative reactive or imaginary or like negative conflicts, it's gonna be like a capacitor in parallel, and then when it's actually when it's positive, well, when it's negative, it's gonna be in series. When it's positive, it's gonna be in
Yes.
parallel. So how do you translate that for inductors?
To where? To translate it into what?
For inductors, does that stay the same?
For inductance, if you have a load that has a positive reactive part, if you have an impedance load that has a positive reactive part, is for impedance is a series combination of a resistor and an inductor. If you have an impedance that has a negative reactive part, is a series combination between a resistor and a capacitor. If you have an inductance with a real and a positive a reactive part, is the shunt combination of a conductance and a capacitance. If you have an admittance that has a real part and then a negative imaginary part, then is the shunt combination of an conductance and an inductance, and an inductor.
Okay.
Okay.
So when you say conductance, you mean like G?
Yes. Usually the conductance is like the inverse of the resistance.
Right.
Yeah.
So
It's
the
a
only
resistor, a conductance is nothing else but a resistor. And we're using the inverse of the resistance just for the formula.
right.
Yeah.
So the sign is going to be the same for the imaginary part. The only thing that changes is the G. Like for example, if I have a resistance in like for the load, I have a resistance and an inductor in series, I'm still gonna have like a real part minus imaginary part.
No, if it's, you mean for an impedance?
Yes.
No, I mean, if it's a series inductance, it's a resistor plus a j omega L.
Okay. Do you mind if I ask, like, could you write it down so I could like visualize it better?
Yeah. So, here, 4 combinations. One is this. The other is this. One is this. And the other is this. Okay, now let me do this, move this a little lower. So for series, I'm writing that the total impedance is R plus J omega L. And here, because they are shunt, I'm writing, this is load, say, all right? That the total load as an admittance is G plus minus, because this is an inductor, minus J omega L. Minus, excuse me, 1 over omega L. Okay? And when I have, so that's negative here. When I have this in the series, I'm always going for impedances. That is R minus J over omega C. And this one, YL, is G plus J omega C.
Okay, so it's kind is like flipped for both of them. So for capacitors and for series capacitors is gonna mirror, well, not the real part, but the imaginary part.
Yeah, it's gonna mirror the shunt inductor, right?
Right.
Yeah.
Okay.
Exactly.
All right. Yeah, I just wanted to have the idea.
Yeah.
For that first question, and just to follow up on that, when you did for the shunt in open circuit and closed circuit, you had uh four formulas using Z naught and Y naught.
Yes.
Did you apply that to the Smith chart?
Yes, but indirectly. So in the Smith chart, you don't have to write that. The only reason I wrote it is because, but I will show you how I applied it. All right. So first of all, we had inductances. And so practically we applied this formula.
Right.
All right. Because we found that this one. See?
Okay.
So practically we applied this formula.
And then you use that to get D.
Well, I did not use the formula. I used the Smith chart with the lines. There. I don't need to use the formula. I mean, that's the Smith chart defies, I mean, then defies the reason of using the Smith chart if I want to use formula.
Sure. Okay. I'm still a bit confused because how would you get the Y if you didn't have the D initially in that formula? It has like a cosine.
That's the beauty of the Smith chart. That's the beauty of the Smith chart, that you get the Y before you get the length. Yes, that's how it works on the Smith chart, which you cannot do. That's why the Smith chart can do design, which you cannot do using formulas. You cannot design using formulas. You can only do an analysis. You cannot design using formulas. All right, so that's exactly what it is. Yeah.
Okay. Do you mind if I see that top half again? I'm just trying to wrap my head around why the Y formula was involved.
The only reason the Y formula was involved is in the negative sign. I mean, you can prove the Y, if you get the results from the Smith chart, you can go and prove that this one applies. This one.
Oh, okay. Oh, so you just use the Y to find like the for example, like
on the Smith chart. I used the Y, I found this first, and then I used the Smith chart to find this.
Okay. So the Y was that imaginary portion, and
minus
then
J 1.6. Yes, the
right.
Y.
So you took the difference from that point to
Yes.
like this, the center.
Yes.
Like this. Okay.
Yes. Oops.
Okay.
Yeah. Yeah.
All right.
What I will do, I will upload this right now, and then so you can have access to it. In
Okay.
fact, I will do it right now. So email. Let me do it while you observe me. Yes. Okay. And what I will do, let me see. There is another thing that I will do. that I can do easily from here. Oh, that's the previous. Here. So then share. Okay, so I can put it to save to files. Okay. Ah, no, better. And then I can go. Let me see how I can do that. Okay. Now we can go to modules. I don't know whether I can do this from here easily. Because I will need to, yeah, I have to do it from, let me see. I will stop sharing from this one here. Stop. And then I will share from here, this one. Okay, so here. Here you're gonna find it out under module 8. Here. I will add here file. And then let me see. Okay, so my notes will be there. Let me see, turn it on. Okay, so my notes are here to download them. And then see what we discussed. And I will put the video later tonight.
All right, thank you for this. Thank you for that.
Okay, so tomorrow also I'll send a note. We're gonna have later in the evening. I was thinking like around from 6 to 8, like a review for those who want to need some help the last moment.
All right.
Okay, take care.
All right, you too.
Bye-bye.
Thank you.
Bye-bye. Mm-hmm.